Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we're going to be doing the solutions for self-test 4 Form B. And for those of you who may be joining me for the exercise sets for the first time, the usual admonishment: make sure you've done all of the problems in self-test Form A and tried the problems in Form B before you watch the tape. And now, because we have a lot of work to do, let's go over to the board and see how we can proceed through these 10 problems. The first problem on self-test 4 Form B, and by the way, I have to start off on an apologetic note. Technically speaking, there's nothing wrong with the way the problem appeared, but the way the answer is given, there is a misprint in the problem. The problem in the first edition reads, which of the following is not a common fraction? 5 over 5, 3 over 0, 2 over 5, 9 over 4, or 7 over 0. And if this is taken the way it's read, the correct answer to the problem should be both 3 over 0 and 7 over 0. The answer is given as 7 over 0, and the reason was I wanted this number to appear as 0 over 3. So to make the answer match the problem, change the problem from 3 over 0 to 0 over 3. And basically, remember the key point. Whenever you have a common fraction, the numerator over the denominator expresses what number? The numerator divided by the denominator. It's a ratio. And the only number, as we'll review in a moment, that you can't divide by is 0. So let's take a look. 5 over 5 means 5 divided by 5, which is 1. And the best way to proceed with that is, let's just take a look over here. If we take 5/5 of 10, 10 divided by 5 is 2. 2 times 5 is 10. So we see that what? 5/5 of 10 is 10, which checks with the fact that 1 times 10 is 10. 0 over 3 means what? Take the number, divide it into 3 equal parts, then take none of those parts. So in other words, 6 divided by 3 is 2. 2 times 0 is 0. And all we're saying is 0 divided by 3. See, 0 divided by 3 means what? The number which, when multiplied by 3, gives you 0, and the only number that gives you 0 in the product is when you multiply by 0. 2/5 is not a whole number, but it's still what? 2 divided by 5. And what ratio is that? 2/5, say, of 15. 15 divided by 5 would be 3. 3 times 2 is 6. See, 2/5 is a ratio. It's 2 out of every 5. 9/4 is also a ratio, but you have to be careful how you read it. You can't take 9 out of every 4. What it does mean is that you divide something into 4 equal parts, then take one of those parts 9 times. Do you see what that means? For example, again, in terms of borrowing money, if you go to a loan shark and borrow money and he says, okay, for every $4 I lend you, you have to pay me back 9. That means you pay back 9/4. See, 9 divided by 4. And watch how that works. You see, if you borrowed $8, 8 divided by 4 is 2. 2 times 9 is 18. In other words, if you're paying back $9 for each 4 that you borrowed, if you borrowed $8, that's 4 twice. So you're paying back $9 twice, which is $18. Now, 7 divided by 0 means what? The number which, when multiplied by 0, equals 7. But what happens when you multiply any number by 0? Any number multiplied by 0 is 0. In other words, 7 divided by 0 is undefined because there is no number which, when multiplied by 0, gives you 7. We call that undefined. To look at it in terms of breaking something up into equal parts, the thing already comes in one equal part. How can you break it into no pieces, all of equal size? It already comes in one piece. Okay, let's continue on and see how these work, just to make sure you get the feeling for what a common fraction is, what a ratio is, and when two ratios name the same rate. Problem number 2 says, which of the following is equivalent to 3/4? And don't let the word equivalent scare you here. All equivalent means here is which one names the same rate as 3/4. The first one is 3 plus 3 plus 3 over 4 plus 4 plus 4. 3 plus 3 plus 3 is 9. 4 plus 4 plus 4 is 12. How do we compare 9/12 with 3/4? Well, since 4 and 12 both go into 36. In fact, they both go into 12, but I just happen to pick 36. Let's see how they compare. 36 divided by 12 is 3. 3 times 9 is 27. So at a rate of 9 out of every 12, you're taking 27 out of every 36. 3/4 of 36. 36 divided by 4 is 9. 9 times 3 is 27. So 9/12 and 3/4 both name what? 27 parts out of 36. And by the way, in terms of the lecture, the reason this works is we mentioned that if you take a common fraction and multiply numerator and denominator by the same non-zero whole number, you don't change the rate. Notice that 3 times 3, which is 9, means 3 plus 3 plus 3, and 4 times 3 means 4 plus 4 plus 4. Now, the second choice I give you is to show you that you have to do more than just do the same thing to numerator and denominator. You see, in the second choice, I start with 3 over 4 and add 5 to both the numerator and the denominator. 3 plus 5 is 8. 4 plus 5 is 9. Is 8/9 the same as 3/4? Well, we just saw that 3/4 of 36 is 27. What's 8/9 of 36? 36 divided by 9 is 4. 4 times 8 is 32. 32 out of 36 is not the same rate as 27 out of 36. So 3 plus 5 over 4 plus 5 is not the same as 3 over 4. The third choice is just to invert, tip over the fraction. Instead of 3 over 4, I give you 4 over 3. Can you visualize that taking 4/3 is not the same as taking 3/4? In other words, dividing by 3 and multiplying by 4 is not the same as dividing by 4 and multiplying by 3. But even if you don't understand that, just work it out mechanically. 4/3 of 36. 36 divided by 3 is 12. 12 times 4 is 48. And by the way, that makes sense. 4/3 of a number should be bigger than the original number. So you're taking 1/3 4 times. 1/3 3 times is the whole number, so 1/3 4 times should be bigger than the whole number. So 4/3 of 36 is 48. And that's much more than 3/4 of 36, which was only 27. How about if we multiply the top number by the bottom one and the bottom one by the top one? 3 times 4 over 4 times 3. When you do that, you wind up with 12 over 12. 12 divided by 12 is 1. That should just give you 12/12 of 36 should turn out to be 36. Let's check it. 36 divided by 12 is 3. Times 12 is 36. If you take a number, divide by 12, then multiply by 12, you get the same number back again. And 36 out of 36 is certainly not the same as 27 out of 36. And by the way, we don't have to lock into 36s. Any common multiple will do. For example, let's look at 3 times 3 over 4 times 4. Notice the difference here. It's not a plus sign, it's a times sign. Okay? See, we multiplied the top by 3, we multiplied the bottom by 4. 3 times 3 is 9. 4 times 4 is 16. Is 9/16 the same as 3/4? No, because 4 goes into 16 4 times. If we multiply numerator and denominator by 4, we see that 3/4 is the same as 12 out of 16, which is certainly not the same as 9 out of 16. So you see how we compare fractions. And now to go one step further, I want to see if you can compare them according to size, using pretty much the same scheme that we just used, but only with more to keep track of. See, problem number 3 says, list the following from least to greatest: 2/3, 3/4, 5/12, 7/15, 17/24. And if we write these as adjectives and nouns, you see what we get: 2/3, 3/4, 5/12, etc. And certainly the adjectives, the numerators, are going from least to smallest, but you see the denominations are also changing. For example, 2/4 is more money than 3 dimes, which in turn is more money than 5 nickels. You see, to judge the size, you have to have a common denomination. So therefore, what we want to do in this problem is to find a common denomination, a common multiple of 3, 4, 12, 15, and 24. In other words, if you're counting by 3s, by 4s, by 12s, by 15s, and by 24s, what numbers will be on all of these lists? And to make the arithmetic easier, what's the smallest number that will be on all of these lists? That's what we have to do here. And the way we do that is we break each of the denominators into prime factors. You see, the 3 is already a prime. 4 breaks down into 2 times 2. 12 breaks down into what? 2 times 6, but 6 is 2 times 3. So you can check this. 2 times 2 is 4 times 3 is 12. 15 breaks down into 3 times 5. 24 breaks down into 2 times 12. And 12 we just saw was 2 times 2 times 3. So 24 is 2 times 2 times 2 times 3. And if you don't feel that confident and want to go more slowly, do it that way. 2 goes into 24 12 times. 2 goes into 12 6 times. 2 goes into 6 3 times. So 24 is 2 times 2 times 2 times 3. Now, how do we find the common denominator? For 3 to go into a number, it at least needs a 3. For 4 to go into it, we need 2 factors of 2. Okay? For 12 to go into the number, we need 2 2s and a 3. Don't we already have that here? We already have the 2 2s and the 3. We don't need anything else. What do we need for 15 to go into the number? We need a 3 and a 5. We already have the 3, so all we need now is the 5. And for 24 to go into the number, we need 3 2s and a 3. We already have 2 2s and a 3, so all we're missing is one more 2. So altogether, what number are we looking for? 3 times 2 is 6, times 2 is 12, times 5 is 60, times 2 is 120. So in other words, if you were counting by 3s, 4s, 12s, 15s, and 24s, the first number that would be on all 5 of these lists would be 120. And that's how we start this problem. To compare those 5 fractions, we rewrite them as equivalent fractions, all of which have the same denominator. See, the least common denominator is 120. 3 goes into 120 40 times. 40 times 2 is 80. You see what we did here? We essentially multiplied numerator and denominator by 40. 4 goes into 120 30 times. If we multiply downstairs by 30, we have to multiply upstairs by 30. 3 times 30 is 90. See, at a rate of 3 out of every 4, you're taking 90 out of every 120. 12 goes into 120 10 times. 10 times 5 is 50. See, at a rate of 5 out of 12, you're taking 50 out of 120. 15 goes into 120 8 times. You can check. How would you do that if you weren't sure? Just divide 15 into 120. It goes 8 times. 8 times 7 is 56. So at a rate of 7 out of 15, you're taking 56 out of 120. 24 goes into 120 5 times. 17 times 5 is 85. See, now I have a common denomination. I have 80 of something, 90 of the same thing, 50 of the same thing, 56 of the same thing, and 85 of the same thing. So now I can look at the numerators and list them from smallest to largest. In other words, the only time that I can be sure that 3 coins outranks 2 coins is if all the coins have the same denomination. You see, 3 nickels doesn't outrank 2 dimes, but 3 dimes outranks 2 dimes. So watch what happens now. The smallest number here is the 50, so that makes 5/12 the smallest. After 50 comes 56. After 56 comes 80, so that's the 3rd smallest. After 80 comes 85, that's the 4th, and the biggest is 3/4. So according to size, how would they be listed? 5/12, 7/15, 2/3, 17/24, and 3/4. You get the idea? It's neat. Notice how we're doing whole numbers here. Once we get that common denominator, all we're doing is looking at the numerator. And the numerators are whole numbers. See, same thing over here. Let's look at problem number 4. 4 comes in 2 parts. The first is just a straightforward mechanical drill problem. The second part is a very wordy thing where the words might frighten you, but once you can read it, it's a very simple problem to do. See, the first problem says, how much is 3/7 plus 1/5? You see, the 3 is modifying sevenths, the 1 is modifying fifths. So we can't say 3 plus 1 is 4. For heaven's sakes, by this stage of the game, don't write 4/12. You can only add fractions when you have the same denomination. Okay? You don't say 1 nickel and 1 nickel is 2 dimes, because 1 and 1 is 2, and a nickel is a dime. You only add common denominations. So what is a common denomination for 7 and 5? 7 times 5, which is 35, is the 7th multiple of 5 and the 5th multiple of 7. So you see what we do here? We say 7 goes into 35 5 times. 5 times 3 is 15. Then we say 5 goes into 35 7 times. 7 times 1 is 7. Now that we have a common denomination, we have what? 15 35ths and 7 more 35ths. So 15 35ths plus 7 35ths is 22 35ths. Remember, 15 plus 7 is 22 whenever 15, 7, and 22 are adjectives modifying the same noun. So what we're saying is 3/7 of a number plus 1/5 of a number is the same as 22/35 of a number. Going back to our lecture when we talked about getting people to back you, if one man gives you 3 out of every $7 you spend and the other one gives you 1 out of every 5, between them they're reimbursing you $22 out of every 35. At which point somebody says, but aren't there other things other than going into business? And the answer is yes. Here's another one. You spend 3/7 of your take-home pay on rent and 1/5 on food. I'm just making those numbers up. I don't know what you spend. But whatever it is, you may not even know. That's sometimes why people go broke. They just spend and don't realize that when you're spending more than you're making, you're going to have a deficit. But basically, that's what budgeting is all about. So assume that you know that you're spending 3/7 of your take-home pay on rent and 1/5 on food. The problem says if you take home $210, how much do you spend on food and rent? Remember, fractions are adjectives modifying nouns. You're spending 3/7 of your take-home pay on rent. But your take-home pay is $210, so you're spending 3/7 of $210. 210 divided by 7 is 30. 30 times 3 is 90. See, at a rate of 3 out of every 7, you're spending 90 out of every 210. Now, you're also spending what? 1/5 of your money on food. So your take-home pay is 210. 1/5 of 210 is 210 divided by 5, which is 42. You spend $90 on rent, $42 on food. 90 plus 42 is 132. Didn't this look like a whole number problem? But what you were really doing was what? You were adding 3/7 plus 1/5 of 210. Now that looks scary. Now it looks like a fraction problem. But let's check it out. What is 22/35 of 210? 210 divided by 35 is 6. 6 times 22 is 132. See, at a rate of $22 out of every 35, out of $210, you're going to spend 132. By the way, very often a person does the problem in reverse. He doesn't know that he's spending 3/7 of his pay on rent. What he says is the reverse. He says, hey, I'm spending $90 a week for my rent. My take-home pay is $210. So I'm spending 90 out of 210. That's 90 over 210. That's 9 times 10 over 21 times 10. We cancel the 10s. That's 9 over 21. 9 breaks down into 3 times 3. 21 breaks down into 3 times 7. We cancel the 3s and we say, hey, at this rate I'm spending what? 3/7 of my take-home pay on rent. So if I want to keep that rate, if I get a raise, what do? I move into a more expensive apartment. How much can I afford? 3/7 of whatever my new take-home pay is. Do you see how you use this stuff? See, I don't care which way you do the problem. I just want you to get a feeling so that when you see 3/7, you're saying 3 out of every 7. Okay? Now, here's a lengthy problem, but again, it's just to show you how even in modern times, certain problems are still hard to solve. And secondly, I wanted to show you in a computer age what kind of problems the computer does the best. See, we're looking in this course for prime numbers because that's how we find least common multiples. So problem number 5 says, list all the prime numbers between 60 and 70. One way of doing this is you list all the numbers from 60 to 70. Now, any number that ends in 0, 2, 4, 6, or 8 cannot be a prime number because it's divisible by 2. So we cross out all of those. Any number that ends in 0 or 5 can't be a prime number because it's divisible by 5. So we cross out 65. Any number, the sum of whose digits is divisible by 3, is divisible by 3, so it can't be a prime number because it's a multiple of 3. Well, notice that 6 plus 3 is 9. That makes it divisible by 3. 6 plus 9 is 15. 15 is divisible by 3, so 69 is divisible by 3, and that leaves us only with 61 and 67 left as candidates. The next prime number is 7. 7 doesn't go into 61 a whole number of times. 7 doesn't go into 67 a whole number of times. But you know, if the product of two numbers is 61 or 67, one of the prime factors has to be less than 8 and the other one has to be more than 8. Because look, the first prime number that's less than 8 is 7. 7 times 7 is only 49. The first prime number that's bigger than 8 is 11. 11 times 11 is 121. So in other words, 49 is too small, 121 is too big. So if the product of two prime numbers is in the 60s, one of the primes has to be less than 7, one has to be more than 7. Since we've already tested all the 1s through 7, we can conclude that 61 and 67 are the prime numbers. Now I'm going to do a very messy thing, but I just wanted you to see how this works. I want to show you the procedure for making sure that you can find all the prime numbers between, not just between 60 and 70, but all the way up to 70. That's one of the problems that we have. Basically, to find a particular prime number, the only neat way is to find all of them up to a certain point. Remember what I showed you in the text? We don't count 1. We start with 2. Any multiple of 2 can't be a prime number because it's divisible by 2. So now I can cross out what? 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Don't feel sorry for me because I picked this messy problem. I feel sorry enough for myself. The reason I picked this is to show you the difference between a difficult problem and a tedious problem. You see how fast the computer could sort through this? I have to do it slowly because even though I don't look it, I'm only human. But a computer goes through this very rapidly. See, now you come to what? The first number which hasn't been crossed out or circled, that's a 3. Now you can cross out what? All the multiples of 3. That's 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51. See, I'm counting by 3s. 54, 57, 60, 63, 66, 69. The next number I come to is 5. I can now cross out what? All the multiples of 5. That's 10. See, if they're gone, I don't cross them out again. 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70. The next number I come to is 7. So now I can cross out all the multiples of 7. What are they? 14, 21, 28, 35, 42, 49, 56, 63, 70. And now my claim is that all the numbers that are left on the list must be prime numbers. Because remember what we said? See, this number only goes up to 70. 7 times 7 is too small to be 70. 11 times 11 is too big. So if a number can be factored into prime factors, at least one of the factors has to be 7 or less. So now I've found what? If I circle the numbers that are left, which I won't bother doing, all the numbers that are left are the prime numbers between 1 and 70. And all I needed was what? The ones that were between 60 and 70. So I look. There's this number, and by doing the problem this way, I've not only solved the problem, but I've found all of the ones that are less than 70. Now, why do we use prime factors? Because prime factors allow us to break down big numbers into products involving smaller numbers. And that's all problem number 6 asks us to do. Problem number 6 says, write 31,680 as a product of prime numbers. Well, how shall we start? Notice that the number ends in 0. Any number that ends in 0 is divisible by both 2 and 5. 2 times 5 is 10. That means I could divide this by 10, but 10 isn't a prime number. See, 10 is 2 times 5. Remember what a prime number is. It's divisible only by itself and by 1. See, I could have decided to divide by 2 first, in which case 31,680 would be 2 times 15,840. See, but 15,840 isn't a prime, so I could break that down further. How do I know it's not a prime? Ends in 0. It's divisible by 2 and 5. I could have divided by 5 first and got 6,336. See, 31,680 is also 6,336 times 5. How do I know this isn't the end? See, 5 is a prime number, but this one can't be a prime because it ends in 6. And any number that ends in 6 is divisible by 2. Well, you see, the beauty is, even though I can factor this in many different ways, if I stick to primes, I can only factor it in one way. See, suppose I decide to divide by 2 first. Then I get 15,840. That means that 31,680 is twice 15,840. Now this ends in a 0. I'll decide to divide by 2 again. So 2 goes into 15,840 7,920 times. Just to show you I don't have to keep going in order, since this ends in 0, I can elect to divide by 5 now. 5 goes into 7,920, 1,584 times. Since this still ends in a 4, I know I can divide it by 2 again. When I do that, I get 792. This still ends in a 2, so it's divisible by 2. I divide by 2 again, I get 396. This being even, I can divide by 2 again, I get 198. It's still even, so I can divide by 2 again, now I get 99. 99 is divisible by 9, of course, but 9 isn't a prime number. 9 plus 9 is 18. 18 is divisible by 3, so 99 is divisible by 3. 3 goes into 99 33 times. 3 goes into 33 11 times. 11 is a prime number. And now I don't wish this on you, but to check this out, what you should do is what? Multiply all these numbers together, and that should give you 31,680. So you have what? 6 factors of 2, 1, 2, 3, 4, 5, 6, 2 factors of 3, 1 factor of 5, and 1 factor of 11, okay? Now, how do we use this kind of information? To find a least common denominator. I'm not going to give you problems this hard to work with. Let's pick something slightly easier. Problem number 7, part A says, find the least common multiple of 15, 35, and 63. In other words, if you're counting by 15s, by 35s, and by 63s, what is the first number on the list that you come to? Now, one way is to list all the multiples of 15, all the multiples of 35, and all the multiples of 63, and see what happens. But there's an easier way if you'll use prime factors. See, 15 breaks down into 3 times 5, doesn't it? 35 breaks down into 5 times 7. 63 breaks down into 9 times 7, and 9 in turn breaks down into 3 times 3. See, 6 plus 3 is 9, so that's divisible by 3. 3 goes into 63 21 times, and 21 is 3 times 7. See the check? 3 times 3 is 9, times 7 is 63. But the important point is, these are all prime factors. So watch what you do. You say, look, since 15 is 3 times 5, 15 won't go into the number. 15 won't go into the number unless that number has 3 and 5 as factors. So the first thing I have to hope for is that 3 and 5 are factors. Once 3 and 5 are factors, I look at 35. What does 35 require? 5 times 7. Well, I already have the 5. All I need is the 7. What do I need for 63? 2 3s and a 7. I already have 1 3 in the 7, so I'm missing 1 more 3. Let's figure this out. 3 times 5 is 15. 15 times 7 is 105, and you don't have to do that in your head. You can go back to Module 3 for that. And 105 times 3 is 315. And in fact, you see, since 15 is 3 times 5, if I cover that up, notice that what's left is 21. In other words, 315 is 15 times 21. It's also 35 times 9. See, if I take out the 5 times 7, I'm left with 3 times 3. And if I take out the 63, see, 63 is what? 2 3s and a 7. If I take out the 2 3s and the 7, I'm left with a 5. So 315 is also 63 times 5. And what that tells you in plain English is that when you're counting by 15s, 315 will be the 21st number in the list. When you count by 35s, 315 will be the 9th number in the list. When you count by 63s, 315 will be the 5th number in the list. And can you visualize if you were trying to do this the long way, you might have got tired and quit before you listed the 21st multiple of 15? See, once I've done this problem, I can now proceed to part B. In fact, if I hadn't done part A yet, I would now have to do it in order to do part B. Because part B says, express this sum of fractions, 4 15ths plus 2 35ths plus 8 63rds, as a common fraction in lowest terms. One of the things I'm going to show you is that you don't need parentheses here, but for parts B and C, I'm putting the parentheses in to emphasize that, that when you're adding common fractions, it's still associative. And the reason for that will be when you get things into a common denominator, all you're going to look at is the numerators. The numerators are whole numbers. Therefore, since addition of whole numbers has the associative property, so will the fractions. But I'll show you what that means in more detail as we go along. See, I want to add this and put this into lowest terms. So what do I need to add here? A common denomination. And in part A, I found that the common denomination of 15, 35, and 63 was 315. Now, how many times does 15 go into 315? It goes in 21 times. See, that's what we found before. We found that 315 was the 21st multiple of 15. Multiply downstairs by 21, I have to multiply upstairs by 21. That gives me 84 over 315. 35 goes into 315 9 times. If I multiply downstairs by 9, I have to multiply upstairs by 9. So at a rate of 2 out of every 35, I'm taking 18 out of every 315. See the whole number emphasis? At a rate of 2 out of 35, I'm taking 18 out of every 315. 63 goes into 315 5 times. If I multiply downstairs by 5, I have to multiply upstairs by 5. See, 63 goes into 315 5 times. 5 times 8 is 40. So at a rate of 8 out of every 63, I'm taking 40 out of every 315. So altogether, out of 315, how many am I taking? 84 plus 18 plus 40. See, technically speaking, I want the 84 and the 18 grouped together. See, because the 4/15 gets replaced by 84 over 315. The 2/35 gets replaced by 18 over 315, etc. But the important point is, since addition is for whole numbers is associative, and since I'm only adding the numerators, 84 plus 18 is 102, plus 40 is 142. 142 what? 142 3/15. Now the question that comes up is, how do I know that this can't be reduced any further? Well, let's see if they have any common factors. We already found that 315 was 3 times 5 times 7. 142 breaks into 2 times 71. Look at what happens here. Even if we didn't know that 71 was a prime number, 3 doesn't go into 71, 5 doesn't go into 71, 7 doesn't go into 71, so no factor on the numerator can cancel with any factor in the denominator, and that means that 142 over 315 is already in lowest terms. Again, going back to a business example, you see, if somebody pays 4/15 of your expenses and somebody else pays 2/35 of your expenses, then you find a third person to pay 8/63 of your expenses. Between the three of them, they pay $142 out of every 315 that you spend. And by the way, part C is exactly the same problem, and I want you to see that. You see, in part B, I found out that 4/15 was the same as 84 over 315, 2/35 was the same as 18 over 315, and 8/63 was the same as 40 over 315. Now what do? I keep the common denominator. You see, pretend the denominator isn't there. Just work with the numerators. See, 18 plus 40 is 58. See, 58 and 84 is 142, because the answer has to come out the same as before, because the addition of whole numbers is associative, so the answer is 142 over 315. On the other hand, subtraction does not have the associative property. See, in problem number 8, you see parts A and parts B. I'll jump ahead here. See, in part A and B, if the parentheses are left out, both look like 5/6 minus 3/7 minus 1/5. But in part A, the 5/6 and the 3/7 are grouped together, whereas in part B, the 3/7 and the 1/5 are grouped together. Let's see what a difference that makes. The first thing I want to do is convert these to common denominations, because before I can add or subtract, I need the same denomination. Well, you see, 6 breaks down into 2 times 3. So for 6 to go into a number, I need 2 times 3. For 5 to go into that number, I also need a 5. So I need 2 times 3, which is 6, times 5, which is 30. But 7 has none of these factors, 2, 3, or 5 in it. So in other words, in this particular problem, there are no common factors to help me here. The least common denominator is going to be what? 6 times 5 times 7, which is 210. And you see, 6 will go into 210 35 times. So at a rate of 5 out of 6, you're taking 175 out of every 210. 7 goes into 210 30 times. So at a rate of 3 out of every 7, you're taking 90 out of every 210. 5 goes into 210 42 times. So at a rate of 1 out of every 5, you're taking 42 out of every 210. Now what you do is go back to the problem and replace each of these 3 numbers by its synonym, which has the common denominator. In other words, 5/6 gets replaced by 175 over 210. 3/7 gets replaced by 90 over 210. And 1/5 gets replaced by 72 over 210. Now I do everything inside the parentheses first, and since I have a common denominator, I can just work with the adjective. See, you can add and subtract ignoring the nouns as long as all the nouns are the same. So 175 minus 90 is 85. Then I subtract 42. That gives me 43. 43 what? 43 2/10. In other words, it's 43 over 210. And that must be in lowest terms because 43 is a prime number. And if you didn't know that, take the 210 and break that down into a product of primes. See, 2 goes into 210 105 times. That ends in a 5. 5 goes into 105 21 times. 2 plus 1 is 3, so 3 goes into 21 7 times. So 210 is 2 times 5 times 3 times 7. And it's easy to see that 43 doesn't belong to either the 2 table, the 5 table, the 3 table, or the 7 table. So this is already in lowest terms. And the answer is 43 over 210. Now, part B is exactly the same problem, only we've switched to parentheses. See, I still replace 5/6 by 175 over 210. I still replace 3/7 by 90 over 210. And I still replace 1/5 by 42 over 210. The only difference now is that inside the parentheses is 90 over 210 minus 42 over 210. 90 of something minus 42 of something is 48 of that same something, so this gets replaced by 48 over 210. If I subtract 48 from 175, I get 127. 127 what? 127 of the common denomination, which is 210. And again, to check whether this can be broken down further, the prime factors of 210 we saw were 2, 3, 5, and 7. And since neither 2, 3, 5, nor 7 goes into 127, that means the problem is already in lowest terms. Now, here's what's important. A lot of times you see a big number and you can't factor it. It's too hard for you. Be careful. As long as one part, either the numerator or the denominator, is easy to factor, then we don't have to worry too much about the other factor. Let me show you the trick to problem number 9. Problem number 9 says reduce 106 over 2,173 to lowest terms. You say, oh my gosh, 2,173. What in the world goes into that? And you could try trial and error, but let me show you a trick. The 106, that ends in a 6, doesn't it? So that's divisible by 2. 2 goes into 106 53 times. So the numerator is 2 times 53. And 53 is a prime number. See, we found that when we found all the primes up to 70. 53 was one of them. Now here's the trick. No matter how this thing factors, you can only reduce a fraction by canceling a common factor. The only prime factors in the numerator are 2 and 53. So unless either 2 or 53 is a factor of the denominator, there's nothing to cancel. Well, obviously 2 can't be a factor of the denominator because it ends in a 3. Remember, the multiples of 2 end in 0, 2, 4, 6, or 8. What's the only other possibility? Something you might never have guessed if you were going by trial and error, but why worry? The only possible thing that's going to help you is 53. So you go for it. You give it a shot. You say, it's not going to take me long to divide 53 into 2,173, and it's a no-lose situation. Because if 2,173 is a multiple of 53, I can reduce this fraction. And if it's not, the fraction can't be reduced. Well, I wouldn't send you on a bum goose chase here. I'm going to make sure this does work for you. 53 goes into 217 4 times. 4 times 53 is 212. 212 from 217 is 5. Bring down the 3. 53 goes into 53 once. In other words, even though you might never have got there in too fast a period of time doing this by trial and error, another name for 2,143 is what? It's 41 times 53. In other words, if you were counting by 41s, this is the 53rd number you'd come to. If you were counting by 53s, this is the 41st number you'd come to. But both 41 and 53 are primes. If you tried smaller numbers, they wouldn't go into this. You probably would have given up saying, if this thing could be broken down, it would have happened by now. But you see, now the thing is what? 53 is a factor of the numerator. 53 is a factor of the denominator. We can cancel that common factor, so the answer to this problem is what? 2 over 41. And notice how much simpler this is. Which would you rather have to keep track of? Taking 106 out of every 2,173 or taking 2 out of every 41? You see the psychological advantage? Even though they're equivalent, one is easier psychologically to handle than the other. And speaking of psychology, we come to our last problem. And that is, no matter how much math you know, it doesn't help you in your own chosen profession unless your profession is being a mathematician. See, mathematics only tells you how to quantify. It doesn't tell you what to do with the result. And let me give you an example. This is kind of a long-winded problem, but there's a moral to it. It says you want to buy 175 items that usually cost 35 cents each. So ordinarily, what am I going to pay in the sale? I'm going to buy 175 items at 35 cents each. That means I'm going to pay 35 cents 175 times. But there's a special sale, and the sale advertises buy 7 but pay for 5. See, for every 7 you buy, you're only going to pay for 5. Doesn't that sound like an exciting sale? Wow, they're going to give me 7, but I only pay for 5. All right, what does that say in the language of fractions? Or better still, does this sound like a fraction problem? Buy 7, pay for 5. There's no fractions in there. There's whole numbers. But now listen to that problem. Since you're only paying for 5 out of every 7, you're only paying for what? 5/7. How many are you buying? 175. So what are you doing? The key point is you're paying for 5/7 of the items. Since you were buying 175 items, you see the adjective noun thing here again? You're paying for 5 out of 7, but how many you're paying for still depends on how many you're buying. What is 5/7 of 175? I take the 175 and divide that by 7. So you divide by the denominator, multiply by the numerator. 175 divided by 7 is 25. 25 times 5 is 125. So what this says is, I am only going to be paying for 125 of those items. So what am I going to be doing? I'm going to be paying 35 cents 125 times. So I simply multiply the 125 times 35, get 4,375 cents, which is $43.75. By the way, it didn't occur to me to do the problem the way I'm going to describe now, but you could have done it this way. What you could have done is said, I'll multiply the 175 by the 35, because that's what it would ordinarily have cost me. And now I'll take 5/7 of that cost. See, whether I'm counting by items or counting by cost, I'm only paying what? 5/7. So I could have taken what? The regular price and taken 5/7 of that price. And an equivalent way of doing that is to say, look, instead of paying 35 cents an item, isn't it the same as if I'm only paying 5/7 of 35? See, 35 divided by 7 is 5. 5 times 5 is 25. So now what I'm saying is what? It's the same as if I bought all 175 items. I paid for all 175, but I'm only paying 25 cents each. 175 times 25 still gives me the same what? $43.75. I thought you'd like to see a cute computational trick here. Notice that 25 is 100 divided by 4. So a very quick way to multiply by 25 is what? Multiply by 100, that means tack on 2 zeros, and then divide by 4. So if I took 175, tacked on 2 zeros to get 17500, then divided by 4, you see what I get over here? See, 4 goes into 17, 4 times the remainder of 1, 4 goes into 15, 3 times the remainder of 3, 4 goes into 37 times with a remainder of 2, 4 goes into 25 times. There's my same $43.75. And here's where I bring out math versus advertising. There are many different professions you might be in or that you're planning to go into. I just pick a typical one just to show you the difference between knowing your field and knowing mathematics. See, you've decided by knowing math that you're going to give a 5/7 sale. You're going to do what? For every 7, you're going to deduct 2. But you want to say that in a way that's going to be attractive to the customer. For example, should you say that each item is marked down from 35 cents to 25 cents? Isn't that what effectively happened? See, since you're only paying 5/7, 35 divided by 7 was 5. 5 times 5 was 25. But you also could have said what? Buy 7, pay for 5. Which of these two sounds more catchy? I don't know. That's why I'm not in advertising. But the person in advertising first has to know the math to recognize that both of these two things say the same thing. Then comes the psychology of buying that says which of these two is going to be the better turn on. You see, you can study anything you want, but the bottom line is what makes a person buy your product. Only one of the ingredients is price. It could be color, it could be the shape of the package, it could be the size of the print, it could be all kinds of things. But mathematics only helps you answer certain quantified problems about a particular situation, and it is not a substitute for understanding what's going on around you. You see, in this sense, math is just one of many subjects you have to know to be able to progress through the real world. And with that as a background, I'd like to stop over here, tell you to look forward to our next lecture, Module 5, on common fractions, and until that time, continue to have fun, study, and stay young.